All right. So screen sharing. All right. Put this stuff down here. Guess it doesn't like to go all the way to the bottom, does it? All right. Try it there. Okay. So basically, the radio involves transmission of information by uh, generating and receiving radio waves with some information on them. Um, CW is the basic example where you turn it on and off. Digital modes do a similar thing, although usually modulated with a tone or multiple tones. And then in the voice or audio case, you're using voice audio in order to modulate it, either AM or FM, or in some cases, phase modulation. The electromagnetic waves are composed of an electrostatic field, which we call the E field, an electromagnetic field, which we call the H field, and they're perpendicular to one another. If you see in the little picture, uh, they're showing the red electrostatic field. In this case, it's a horizontally polarized wave. The magnetic field is 90 degrees from that, or vertical. We mostly deal with the electrostatic field. Now, if you have I guess, a magnetic loop, it's receiving the electromagnetic wave. But if you've noticed on that, did you see the video last week?
Mhm.
And they showed how the magic of it releasing the uh, electric, electrostatic wave.
Mhm.
Uh, and that's mostly what we deal with. I can't tell you much about a magnetic loop other than they're getting popular, they're expensive, uh, they're extremely narrow band. So you have to be able to tune it if you want to move around in frequency. They won't cover an entire band, even the narrowest bands.
So what's the advantage of it then? Is there any?
Well, they're small. I mean, you can put it in a room, put it in the attic. Um, Apparently, they have pretty good gain, and especially people in HOAs or apartments or something like that. You can sit on the balcony. Um, I mean, there's a lot of advantages to it. I mean, a lot of people can't put up a tower.
Right.
Well, I guess we'll do this one. It's a lot of repeat. Maybe we will. Thing on the internet. But while we're waiting, the key thing is that 90 degrees apart between the electrostatic and electromagnetic. You don't have to remember those. I like their electron, their atom.
All right.
Huh?
Don't hesitate to donate.
Yeah, they like their money. Uh, that feed horn they showed on the dish antenna is actually an impedance transformer, which is what we would use with a regular wire wound transformer for most of our antennas. But it does the same kind of thing. I don't know what the natural impedance of that dish would be, but that's how you match it to free space. So which is 377 ohms. So it's going to match 377 down to whatever that is.
Okay.
Okay, so what are the two components of a radio wave?
See.
What's the relationship between the electric and magnetic fields of an electromagnetic wave?
Indeed.
Right angles to each other. Yeah.
Yep.
A is turbo.
A? What was A?
They, no, they both.
No, they don't. They're together. They stay in phase. Well,
So,
sort of in phase.
so they stay in opposite phase, but it's still a phase.
Right.
Right. It doesn't change.
Right.
Right. Okay. So I don't know if we talked about frequency, but it's the number of complete cycles per second, which means polarity reversal of the current. We measure it in hertz, named after old Heinrich Hertz. Use the capital HZ. That's a trick question. They'll give you 4 variations, and you have to pick the one with the capital H in it.
Because it's a proper name. Is that what?
Because it's proper name. Wavelength is the distance the wave travels in one complete cycle. It's assuming that it's traveling at the speed of light. Now, when you get to it actually traveling in wires, it's a little bit slower. So there's velocity factor that you apply. So you'll see a 0.95 come up in some of the calculations, because that's typically what it would be in a bare copper wire. Now, it's much slower in coax. And if it's insulated copper wire, it's a little bit slower because it changes the dielectric.
Is that because of the resistance?
No, the dielectric changes, so the capacitance changes. And the speed of light is 299,000, blah, 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 or approximately 300 million meters per second, which is what we use, is close enough. And if we deal frequency in megahertz, then we can cancel out the million and make it 300 versus whatever the frequency is in megahertz. So it makes the formula real simple. And it only travels at that 300 million in free space, which means, and basically it means a vacuum. To calculate it, and we use the symbol lambda, which is that funny looking thing. We divide the speed of light by the frequency, and that will give us the distance or the wavelength. So instead of doing the 300 million, with the frequency in hertz. Like I said, we reduce it down to 300 over the frequency in megahertz. Conversely, if you swap it around, if you want the frequency, you divide 300 by the wavelength. So you can go back and forth just by reversing the formula. The lower the frequency, the longer the wavelength. The higher, the shorter the wavelength. Test question.
It kind of makes sense if you look at a sine wave.
Right. And if, look at the way you divide it, the
Mhm.
higher number is going to make it shorter. There's a little example here. The wavelength for about the middle of the 40-meter band, which would be 7.150. It goes from 7 to 7.3. So that comes out 41.95 meters, and we call it the 40-meter band because it's an approximation.
Okay.
In this example, we're doing the frequency for the 20-meter band, and it comes out 15 megahertz. It's actually 14 something in practice, the frequencies. 14 to 14, might be 0.3. I actually can't ever remember all those. But unfortunately, some of them are on the test.
For the practice test coming in handy.
That's why you have the little cards. What is the velocity of a radio wave traveling through free space? Speed of light. What's the approximate velocity of a radio wave in free space?
Three times 10 to the 8.
Huh?
6.
Well, it's 3 times 10 to the 8 meters per second.
Yeah.
That's
Three,
all I.
three times 10, right?
Yeah. But they're using 300 to the 6.
Well, and that way it comes out megahertz.
Megahertz.
What's the formula for converting frequency to approximate wavelength? So in other words, you're solving for wavelength.
Would be D.
There's Ernie. Which one are you going with? Oh, okay. All right. What's the relationship between wavelength and frequency?
D.
Yep.
We're doing test questions.
I didn't hear you.
We're doing test questions.
Oh, okay.
I'm sure you know all these.
Majority of them.
Does everybody know Ernie?
No. I'm Aaron. For K1CTO. Steve. Roger.
Yeah.
He's going to help us with our hands-on a little bit later. And Dave is got his radio. So
He's gonna break by.
no,
Oh,
he's working. So he'll answer if there's nobody around. Otherwise, he get in trouble. But we can also talk to Michael on the KSC repeater. He's got his radio, and I checked with him earlier.
Okay.
Okay. The relationship between wavelength and frequency.
That would be. The shorter end.
Sounds good to me. Okay. Radio frequency is, as far as the exam is concerned, a radio signal of any frequency or any mode. It's just kind of a generic term. Why that's a question, I don't know, but I guess they have to fill up the 400 and something questions with something.
Well, they cut down this new list just come out. They got rid of 40 questions starting this July.
Oh, for the general?
Yeah.
Oh, I hadn't compared it yet. I've got to do that.
Hmm.
Okay. We use both frequency and wavelength when we talk about radio signals. Basically, wavelength to represent bands of frequencies because it's easier than talking about specific frequencies. When you're talking about a particular band, then you might talk about it being, 7.074 or something like that. And they're kind of used interchangeably back and forth. That's why you need that formula, but you can pretty much do it in your head to get close. I mean, 20 meters into 300 is about 15. This example, the 2-meter band goes from 144 to 148. So if you do the math, it comes out 2.03 meters. So these are always approximations. They're never exactly the right number. Usually it's off the band. But, it's something that's you get used to. It just becomes kind of second nature if you played with it for a while. We split up this range of frequencies that we use into these sub-ranges called medium frequency, high frequency, very high frequency, ultra high frequency. And I guess now they're doing super high frequency and whatever the one is beyond that. I'm not sure. And also, I guess, low frequency.
For low.
Yeah. That's the club just put up 160 meter wire out at KSC.
Listen to submarines or something?
I don't know, but the 630 and what 1200 something meters.
Yeah, it's 135 kilohertz one. That's the very low one. And when you're allowed 1 watt, that's radiated power. It's
Well, if you got
it's what the utility companies use for transmitting data. That's why you have to file a claim or get permission from the utilities to use those ultra low frequencies.
I did not know that.
Now, you have to sign up before you can use it.
Okay. Well, supposedly that low stuff is getting popular. I don't know.
I don't know, never tried.
Okay. This you probably can't see too well, but it's just showing it's a reduced form of these other band charts, just showing the technician privileges, where at HF, you have phone and data and SSB, CW, all those on the low end of the 10-meter band. That's the only HF where you can operate phone. For VHF and UHF, it's pretty much the entire bands, except for that 1.25 meter, which I don't know who uses that other than, I guess it's communications repeaters mostly, isn't it?
I don't.
Back channel.
Remember.
And you're limited, I believe, on these VHF, UHF to 1500 watts, 200 watts on the HF. Now you can do CW on the other HF bands if you know CW, but it's not required anymore. But I understand that's getting popular again, particularly in the QRP world. This is this showing what frequency ranges are. Medium frequency is 300 kilohertz to 3 megahertz. So the 160 meter band is going to be in there. HF, which is what we normally do, particularly phone, SSB, is 3 to 30. These all go up by tens. VHF is 30 to 300. That one will come up again in the safety because that's the maximum exposure frequency band. Your body is most susceptible at 50 megahertz. So that entire 30 to 300 is the minimum exposure you're allowed. And UHF is 300 to 3000. Okay, in addition to frequency, which of the following is used to identify amateur radio bands?
Okay, we didn't talk about the other two, so I'm gonna guess it.
Yeah. Uh-oh.
Not on that, Joe.
Clicked on the wrong spot. Good. What frequency range is referred to as HF?
See,
Over the three. Mhm.
HF.
okay, so
3 to 30. The 40 meters is 3.5 megahertz. 10 meters is 29, 28 to 29.
We need something.
Yeah. I don't remember them either,
I don't remember.
but you should. You've been doing it for years.
Doesn't mean I can. It shows up in your radio.
Oh,
Predetermined,
huh?
predetermined selection.
Yeah.
Yeah.
I skipped ahead, but VHF is 30 to 300. Like I said, that comes up on the exposure calculation. But it's also a question in this group. What frequency range is UHF?
No. Mm.
What does the abbreviation RF mean?
okay,
See, I told you they had that question, but I don't know what it serves. Okay. Propagation modes. This is fun stuff. Hopefully you know more about it than I do, Ernie.
A little bit.
The atmosphere can refract or bend radio waves depending on the angle and the frequency and solar conditions, how much ionization there is, which is oxygen atoms in the upper atmosphere. When there's enough high energy particles hitting them, can displace electrons and create positive and negative ions. And those interact with radio waves and can bend them, like light gets bent through different types of glass or other material because of the diffraction index, refraction index, I should say. So it's a similar thing to the way light works, because light is just very high frequency radio waves. So some of them will actually bounce off. Some will go straight through, like UHF and above. Typically, there's no refraction. At least is my understanding.
That's very little.
Some on VHF. So they're not propagated, which means you don't get any sky wave where it gets refracted and bounces back down and then bounces up off the earth, and maybe do it multiple times. You can get all the way around the world sometimes.
Not call it skip anymore.
That's called the skip. It's how far it goes.
Yeah. And unfortunately, when you're doing that region in between,
You're skipping it.
nobody hears your signal. Unless it's a very broad band and it's scattering all over the place.
So it's kind of like driving up 95 with an FM radio station on, if two towers are transmitting two different radio stations, they kind of alternate as you get further away from one and get closer to the other.
Mhm.
Yeah. Okay, so most VHF, UHF is what we call line of sight, which means you have to be within visual, assuming there were no buildings, trees, whatever, okay, that you could see the other antenna. And there's a formula for calculating that based on the radius of the Earth and how high the antenna is to where the visual horizon is. And that's this 1.23 times the square root of the height of your antenna. So if you've got a handy talkie and you're a tall person, say it's 6 feet above the ground, then it would be the square root of 6 times 1.23, and that would give you how many miles to the horizon. Now, if you're talking to somebody who's the same height, okay, you got twice that distance. So it's yours plus theirs, wherever they are. Now, because there is some refraction of VHF, they come up with a fudge factor, and they use 4/3 of the Earth's diameter in the equation. And it comes out to be, it's actually the square root of 2 times the height in feet. So it's 1.414 times the square root of h. So it gives you about 15% more. But does that only apply to VHF or also UHF?
About to say they call, when we were native, it's 5/4 what we used.
Yeah, the latest stuff I read said 4/3.
20% more.
I think it's a fudge factor.
Yeah,
It's approximation. But basically, because of the refraction, the waves can actually travel farther, and we call that the radio horizon as opposed to the visual horizon. This little diagram showing, here's what that distance would be when you calculate it, and when you're talking to somebody else, it's the sum of the two, which would be the total distance.
So with lower frequency travel farther, like if you're in the HF range,
ground waves, they go out. They've been more UHF and
Yeah.
VHF.
Yeah, HF works different. And there's a big difference in frequency here. So,
Yeah,
okay, why is the radio horizon for VHF and UHF more distant than the visual horizon?
see,
Okay. Why are simplex UHF signals rarely heard beyond their radio horizon? So what they're referring to is you're not going through a repeater. You're talking on the same frequency as somebody else with another radio.
reason they say rarely, because sometimes you do get a reflection or tropospheric conditions will make the radio wave go around.
should we see
Hmm?
on this one?
See what you. One there, and see what you.
Usually not propagating.
There's always exceptions to everything. Okay, multipath. That's where you can have multiple signals arriving at your receiver, even though they came from the same transmitter, because they can reflect off of buildings and other things. So you get that signal coming 2, 3, 4 different ways, and they get there at different times. So they can add or they can subtract, and they can cause echoes, very short echoes, but definitely cause some distortion. Just by moving a few feet one way or the other, it means you'll change the pattern. And that's where, and that can cause the signal strength to vary greatly depending on where you're at and if you're moving, which is the picket fencing Usually you see that if you're mobile in a car. And because you're getting multiple things, it'll kind of sound like you're going by a picket fence, da, da, da,
Choppy.
because it comes and goes and comes and goes. Uh, when you're doing digital transmissions, uh, they don't work well in those conditions. Because in digital, you either have the full signal or no signal. There's no noisy signal. Whereas with single sideband or AM, I mean, even if it's full of noise, you may still be able to understand what somebody's saying. With a digital signal, you get a good signal or you get a no signal.
Well, it's like satellite radio. I guess.
Yeah. This is just a picture showing potential multipath off of these big buildings. Now, I guess we don't see that much around here. There aren't too many things to reflect off of.
It's like, Verizon is 5G.
It may be. Okay, why do VHF signals sometimes vary greatly when the antenna is moved only a few feet?
Sensor C.
What's the meaning of the term picket fencing?
B.
What'd you say?
I said B.
Oh, okay. I don't hear well. What effect does multipath propagation have on data transmissions? There's data, not voice.
Delta.
Yeah, I was gonna say here.
Repeater access. Normally, you're talking line of sight to a repeater. They're typically on very tall buildings or towers. I guess the highest one around here is the NASA repeater on top of the VAB. It's 526 feet. So if you do that calculation, the line of sight for that is about 30 miles, 40 miles. Uh,
1,000 footers.
huh?
There's not 1,000 footers around here.
Yeah. One
Maybe.
Up in, Bidwell or on, around 50 left. Bidwell?
Bithlo?
Yeah, that's about 1,000 feet up.
Really? Most of them locally or what's
37 is-
broadcast court?
It's about 370 feet or 400 feet, something like that.
Yeah.
And one down in Melbourne is like 400 feet.
Yeah, I can't get that with my handy talkie. At least not in here.
Yeah,
Now there's also an indirect path where it can kind of like multipath reflect off of something else that you don't have a direct line of sight, and you may be able to get the signal to bounce off of something and still get to what you can't see. I'm not exactly sure how that works or how to explain it. I haven't seen it. I'm just going by what they tell me. There's also knife edge diffraction, which I'm familiar with in optical stuff, where you have a very sharp edge, like a razor blade or something, and light will bend around it quite a bit. And I can understand it around the edge of a building, but supposedly something like a mountain peak will do it. I wouldn't consider that a sharp edge, but I guess it works. So with knife edge, you can theoretically get to an antenna that you can't see that's on the other side of that mountain. And then we got absorption. basically anything with water in it, vegetation, people, absorb UHF and microwave signals. So they don't work good in the rain. Anything with a lot of water. It's just a little thing showing typical repeater access where it's up on top of a mountain and you can't see the other guy, so you go through the repeater. When using a directional antenna, how might your station be able to communicate with a distant repeater if buildings or obstructions are blocking the direct line of sight?
Bravo.
Okay. This is one showing knife edge diffraction where it sort of bends the wave, and you can see it down here. They call it the geometric shadow. Which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations?
I'd say A, but B is pretty funny.
Yeah. Fair
And
enough.
we haven't got to satellites yet. What's the effect of vegetation on VHF and microwave?
B.
Sucks them up. Polarization. It's defined as the orientation of the electric or electrostatic field with respect to the Earth. So there is no polarization in free space. When it's on the Earth, depending on whether it's a horizontal or a vertical antenna, will basically give you horizontal or vertical polarization. As long as it's line of sight. If you got propagation and it's bouncing off the ionosphere or possibly even other buildings, the polarization can become elliptical because of some phase shifts.
Space is omni,
Huh?
space would be omni, omnidirectional.
Yeah. Well,
It's nothing
if
but
it's
light.
if it's a dipole in outer space, it's still going to have that donut, but
Yeah.
it's going to be perfectly symmetrical because there's no ground effect or anything. Okay, so for VHF and UHF, for line of sight things, if you have crossed or differing polarizations, in other words, if you got your handy-talkie and holding it up, I'm vertically polarized. Okay, if he's over there and he's got his that way, horizontally polarized, the signal is just going to be the intersection of those two. It's going to be very, very small. Whereas as you rotate them and they line up, because you got matching apertures basically, then you're going to get the maximum amount of signal. In long distance work, and I don't know how you do long distance on UHF, but I don't.
Horizontal.
Right, but I
That's when
mean,
we use sideband on VHF,
who,
UHF normally.
other than satellites, who do you contact long distance on UHF?
There's the.
Because it's line of sight
They use propagation.
for
Basically,
UHF.
On 2 meters, a lot, 4 meters, 2 meters.
Well, that's
People
VHF.
run single sideband
Yeah,
and they use it horizontally
right.
based, and you get some skipping effect.
Yeah.
And it goes with a lot of it with temperature and also with the sun, evening and
Yeah,
morning. They call that.
Solar phase or whatever it is.
yeah. I think there's a chart showing a little bit of that later.
Yeah,
And basically that's because of it. When you get refraction, you're becoming elliptically polarized, basically circularly polarized, except it's not perfectly circular, so it's elliptical because circle is a special case of an ellipse. So it really wouldn't matter, and it's typically easier to do like with the beam antenna horizontal than vertical, which comes up a little later as a question too. And for repeater handheld, normally you want to stay vertical. So if you really want having trouble talking to somebody, you want to try to keep both antennas up or sideways, but they need to be the same. And typically a repeater is always going to be vertical. Okay, here's actually showing the difference between elliptical or circularly polarized and your normal linear, where you got a horizontal and you got a vertical. Now you can transmit both with a crossed antenna and do horizontal and vertical signals. And sometimes they do that for satellite reception because it's not only possibly elliptical, but it's rotating, the Faraday rotation. What property of a radio wave defines its polarization?
Okay.
Yep. Electric field with respect to ground. What happens when antennas at opposite ends of a VHF or UHF line of sight radio link are not using the same polarization?
Problem.
What antenna polarization is normally used for long distance CW and SSB contacts on VHF and UHF bands?
So,
And it's normally because they're doing it with beam antennas, and big beam antennas are, although they wouldn't be that big at VHF and UHF, so I don't know why it would be a problem doing them vertical.
that would be similar to the old TV antennas, right?
Yeah,
Beam
I
antenna.
mean, those typically are Yagis or log periodics. And you always see them horizontal,
Mhm.
but on
The
those,
TV signals are still transmitted with vertical. After a certain distance, they end up being scattered and end up horizontal. Works just as well.
okay, VHF are most often line of sight. There's some modes that can allow you to communicate long distances around the world and more. I don't know if you can do 2 trips. I guess if you had enough power and the right propagation, you could. In fact, I don't know that it comes up in the tech, but in the general or extra, they talk about problem of short path and long path, where you can be talking to somebody 2,000 miles away, but they're also getting your signal all the way around the world, and they obviously come different
Times.
delays. Okay. VHF may bounce off the E layer. And in the chart down here, they define the different ionization layers of the ionosphere as the D layer, which is the lowest one. It's basically an absorption layer because it's got the most oxygen molecules. This is the lowest one. It's the most dense. So it tends to absorb frequencies and it disappears at night, which is why those same frequencies work at night and they don't work very well in the daytime. Then you have the E layer, which will allow some sporadic propagation where it hits the E layer and it scatters. Some of it comes back, some of it comes down, some of it goes up. So it's not very reliable. That's why they call it sporadic E. but you can get over the horizon with it on these upper bands. And the 10 meter is best in the daytime with high sunspot activity. And all these are affected by solar activity, the sunspots and how much radiation is coming out, flares, all that stuff.
You have to go in their light system to get the,
You get more
We have some charts on that.
huh?
We have some charts on that
Oh,
coming up.
oh, I didn't know that.
Isn't that because we have more ionization in the atmosphere?
Yep.
Sunspot activity being higher.
Yes,
Yes.
yes. But it can also blanket everything and
It's over.
send it down the tubes, which happened here just a few days ago, right? Yeah, a
Oh,
week
yeah.
or so. Okay. Oh. I added this and I didn't erase the other stuff. Just look at the picture. It's showing skywave propagation and different angles of what do they call it? Not angle of attack.
Reflection.
Launch angle, I guess. Anyway, depending on your antenna and the pattern, it will have a maximum density, power density at some particular angle relative to the Earth. And usually it's optimized at when the antenna is half a wavelength high. When as it gets lower, the angle tends to go up. In fact, when you get all the way down, then you get into the NVIS, where you're basically shooting straight up, so you can do short range communications. When you get to half a wavelength, then that's about as low as it's going to get. When you get higher than that, it doesn't get much lower, but you start getting additional lobes going up, so you're losing power. So it's less, even though it might lower a little bit, it's not as strong as it was. So the optimum is half a wavelength. Right?
That's where I understand it.
And this, yeah, which you may not be able to read, talking about a dipole at half wavelength. And they're bouncing off the F layer, which are the highest layer, which is split into two during the daytime, the F1 and the F2. At night, it condenses into the F layer. So basically at night, you have an F layer and a E layer. Okay, so auroral backscatter, meteor scatter, tropospheric scatter, all kinds of scatters, and ducting. So auroral backscatter is you bounce a signal off of the Earth's aurora, the northern or southern borealis, which they call aurora borealis or aurora australis. And it's due to the magnetic field of the Earth and the solar wind hitting it, and somehow, ionizes all that stuff and makes a big donut. And you can see it from, I was told, I've never seen it in person. Michigan people can see it.
I've heard of it down as far as Pennsylvania,
Really?
but I've never seen one.
I've never seen it, but I think,
You can't see it
Iceland,
through.
Greenland, when you were stationed in Canada, were you able to see it there?
Oh, yeah, I saw it in Alaska, I saw it in Canada, I saw it in Greenland,
Is it pretty?
green.
Well, that's the way this picture coming up is. Okay.
So it's the Jacksonville area.
A solar flare can cause the auroral zone to increase in density and expand, making it capable of scattering without significant absorption. I'm guessing that under normal conditions, it may absorb more than it reflects, but I Really don't know. It's too far away.
That's right.
I can't imagine you can rely on this.
Yeah, right. That's the thing coming up next. It's distorted, can vary. It's not reliable. Like all these we're talking about here, they're basically sporadic things. Okay, here's a picture of the northern and southern auroras. You can see much more intensity over here on one side, and same thing on the southern one. I don't know why that is, but my
Just
trust.
like you can't see it.
That's probably at the angle of the,
Oh, actually, I didn't. Yeah, you're right. It's brighter over here in the
In the dark area.
time. Yeah,
It's there,
which
but
probably has something to do with the day-night stuff on the other things, like the layers going away.
Mhm.
Okay. Meteor scatter. Now, I've been told that, and I think there's some NASA club members that have done this and bounced off of meteor showers. They leave an ion trail behind them. So if you're at the right place at the right time and the right angle, you can bounce a signal off of it, and maybe somebody will pick it up. But again, it's scatter. Okay, so only a portion of it is going to get somewhere, and it's not very reliable. Certainly not something you could depend on happening. Right. And it's, best on this 6 meter band. It turns out 6 and 10 meters are good for lots of things.
Mhm. I don't use them.
And we have tropospheric scatter. Okay. The troposphere is below the ionosphere. And it can also scatter as opposed to refract waves. And again, it's sporadic. So it's just it may happen, it may not. And there's little things showing where actually most of your signal is just going straight through. And some of it is being scattered down, some of it's up. So what proportion somebody would actually receive, I don't know. But if this is representative, it's very small. Then there's tropospheric ducting, where in the troposphere, you can have a temperature inversion where you get a warm layer of air above a cold layer of air. And it acts like a duct for radio waves, and will actually propagate along that duct, like microwaves do in waveguides, similar kind of thing, except much lower frequency. And I don't know, have any idea what the relative distances are that you can get? Have you ever done tropospheric ducting?
Never did.
Well, you might have and didn't know it.
I could have, but
Okay, there's just another chart showing the warm air, dry air, and the difference in refraction. So it's going to depend on the critical angle. And I don't know if we get into that later, but critical angle is dependent upon other factors, and that's whatever angle or the highest angle that will refract. It's dependent on frequency and the conditions of the ionosphere, whatever it's refracting off of. So those angles will change. So, and it's just like light bouncing off of a piece of glass. At a certain angle, it'll reflect. Higher than that, it goes straight through.
so you mentioned it earlier that water has something to do with the transmission. So on like a heavy fog day, does that interfere with the radio signals?
Microwave and UHF.
Yeah.
It wouldn't affect HF, right?
not to the same degree.
Oh, yeah.
Very minimal.
Which of the following types of propagation is most commonly associated with occasional strong signals on the 10, 6, and 2 meter bands from beyond the radio horizon?
I would say
You know what you mean.
So we have an A,
Okay,
Well, I'll pick B just to be different.
a Baker,
okay,
an Alpha,
A couple of them, D region. And a great line propagation. That's the word I was thinking of before.
oh,
Day and
okay,
night,
yeah, right, gray line. As opposed to the A line.
right.
Well, let's see.
no.
Remember, we talked about sporadic E at the 10, 6, and 2.
So the reason why I didn't think sporadic is because it says most commonly associated.
Yeah.
And
that makes some
I
sense.
was thinking the opposite of the word.
It's kind of a trick question. That way you remember it. If you get that question, I'm sure you get it right.
Mm-hmm.
What is a characteristic of VHF signals received via auroral backscatter?
It's only one sense.
Distorted and vary in strength. What band is best suited for communicating via meteor scatter?
I
Is they call that the magic band?
don't know what they call it.
I think it's 6, as they call the magic band, 6 or 10. One of them. What type of propagation is responsible for allowing over the horizon VHF, UHF communications to ranges of approximately 300 miles on a regular basis? I don't think I talked about the distance. So what would that be?
Let's say,
I know what that thing.
Because we didn't talk about the other ones.
well,
You
yeah,
just,
yeah,
you
two-
still are going like that.
Yeah, but that didn't say how far.
Oh,
I need to go put that 300 miles in there.
I, Dave,
Yeah, because F2 is only during the day.
You
The
get
what?
that a lot.
The F2 is only during the day, right? Because it splits layers.
Well, F1 and 2 are there all, well,
But-
F1 and 2 collapse into F at night. They're not separate. But the tropospheric ducting is down much lower, below the ionosphere.
You also get that when it's sunrise and sunset because you have the two different things. That's ducting down that way.
as the answer to this one.
What causes tropospheric ducting?
See?
Delta, delta, delta. Precipitation. Rain, snow, ice, fog can absorb microwaves, thereby decreasing the range, absorbing the signal, which means it's not going to go as far. Well, it may go as far, but it'll be a lot less energy in it. It has little or no effect on lower frequencies. They don't define lower frequencies, but I would say most of the HF band, it doesn't have much of an effect. What weather condition might decrease range at microwave frequencies?
See?
What's the effect of fog and rain on signals in the 10 and 6 meter band?
Hey,
Well,
no?
Should be little effect on. Yeah.
I missed that one the other day when the guy was taking his test. Because 6 meters is VHF.
That's A would be for UHF and microwave.
So
Very good.
It's kind of okay. Uh, Basically, we rely on propagation at HF frequencies to do long distance reliable communications, where all these things we talked about, all the scatters and ducting and things are not very reliable, and they don't get the same kind of distances. Whereas at HF, refractions off the ionosphere, like I said, you can go around the world. I mean, I pick up Australia, New Zealand easily at 50 watts.
And no commercial aviation, they use the HF band when they're like transatlantic, trans-Pacific.
At 20, 15 meters, those, I mean, actually probably see more Asia and New Zealand, Australia around 17, 15. They tend to operate there more, I think.
Aircraft now are usually satellite communications.
Yeah, they still have an HF antenna in them.
I don't know.
They run up the tail stabilizer.
Ah. Okay. The ionosphere is created by solar radiation. So it's those energy particles or waves, whatever all that junk is that comes from the sun, because it spits out all kinds of things, X-rays and cosmic rays and
Mhm.
and that can ionize the oxygen atoms in the upper atmosphere. It gets down into the D layer, which is the lower part, but because it has to go through a lot of it is energy is absorbed in making ions in the F layers. But since there's more oxygen at the lower layers, then you get a stronger effect, which is why the D layer, I think, absorbs more signal. It goes anywhere from 50 to 600 miles above the Earth. So the F1 and F2 layers are up there in the 4, 5, 600 mile, and they vary depending on conditions. And they just talk about the three, the D, E, and F, which we talked about, D being the bottom, but it's still above the troposphere. Here's one, and here you see the troposphere way down here, like 12 kilometers and below. And the ionosphere, the E and F layers, and I still have never figured out what this graph sort of shows, but you can see the height where the ionosphere is part of the exosphere and the thermosphere, and they're up in the 600 kilometer plus. This is just another chart showing the same kind of thing. The difference between day and night, where you only have basically the E layer and the F layer at night. This is a prettier one, kind of showing the difference in refraction off of the different layers. And that is a function of frequency. Like this one over here is probably a UHF signal. This is just kind of going straight through. The lower frequency signals are down here and they're getting bent by the lower layers. They may get a little farther, the higher the frequency. I'm showing one here where some of them refracted all the way and some of them don't quite make it. This is another one I found showing the day-night differences in frequencies. So here you've got your 80 meter, 3.5 megahertz is, I guess, doing ground effect.
Yeah.
And then 40 meters, it's refracting off of basically the E layer. Your 10 megahertz, which is 30 meters, is getting up to into the F layers. And then they're showing 30, I guess, and above really not being refracted during the day. Wow. I don't think that's entirely true because I was making some 10-meter contacts pretty far away.
These are typical.
And then, of course, at night, things change. Basically, everything's coming off of the F layer. And this is another one showing the difference in 1 megahertz, 20 megahertz, how the distance they go, the hop or skip, whichever you want to call it, changes. Oh, I found a lot of these charts, didn't I? Same kind of stuff.
So in theory, if you were to talk to somebody, let's say on a space station, you want a UHF frequency.
Well,
So you didn't.
basically, the satellites all use UHF, VHF. And one of the things,
They transmit on
yeah,
one is back on another one.
I don't think it's in the tech. One of the questions that will come up is they use a format of U/V or V/U, which is represent uplink versus downlink. So it may have a UHF uplink and a VHF downlink or vice versa. So that is what the UV means, whether it's up, which one's uplink, which one's downlink. And they're, they transmit on those two bands. Which region of the atmosphere can refract or bend HF and VHF radio waves? Good old ionosphere. What is the characteristic of HF communications compared with communications on VHF and higher frequencies?
There we go, sir. Yeah.
Sunspots. Okay, 6 and 10 meter band propagation supposedly is best when there's many sunspots. And there's things where they keep track of that. You can look at it daily of what the sunspot predictions are and what they actually were. It's an 11-year cycle. We're currently in, I think, year 3.
Yeah, it's going up now. It's getting
Right.
better.
So we'll be peaking here in another couple years. So it is getting better. This is the 25th cycle since they started counting them, because it's been going on for a long time, actually. And the more sunspots, the more radiation reaches the Earth, more ionization, which gives more reflection or refraction, which is why it's better for long distance propagation. And also, it allows you to operate at higher frequencies. It increases the MUF.
The muff.
The MUF, the maximum usable frequency, which is another thing that they predict on these based on the critical angle and propagation conditions. What's the highest frequency you can operate at that will still get refracted? Higher than that, it goes straight through. At least that's the way I understand the MUF. And then there's a LUF, which is the lowest usable frequency. And I don't understand that one, why that works.
I don't, never even heard of it.
The LUF, well, it's on the exam. Not this one, though.
Is that extra?
Well, definitely the extra. I think it shows up on general. I get them confused. When we have a person taking the exam and you do it online, I get to watch them answer. And we've had a number of them here lately that do all three. They'll take the tech pass, take the general pass, take the extra. And it sort of is a jumble because you go through and you kind of take the test with them.
Mm.
And even though they can't hear or see you, you're, no, 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 not that one. And then sometimes you get them wrong. It's hard to remember all that stuff. Okay. This one I think is attempting to show the difference between day and night. We're over here in the Earth's shadow, or the night portion, how the D layer totally disappears, the E layer becomes much thinner, and the F layers combine and collapse and actually, I think, get a little lower. Which probably means that you don't get the same skip distance because the layer's not as high. And the higher it is, the farther you're going to get on that hop.
The lower angle.
Well, and a high, even the same angle, if it's higher, it's going to go farther. And at the daytime, you've got all those layers in effect. So, which of the following bands may provide long distance communications? HF. These are UHF. And obviously all these choices are correct is incorrect. Okay, the ionosphere changes throughout the day, especially at night. It's best on the higher frequency bands, the 10, 15, and 20 during the daytime. Now, it's been my experience that 20 operates about the same 24/7.
It is pretty good all the time. 10 and 15. Seems to drop out when you don't have. It's getting better now. Before,
Yeah.
it was a couple of years ago, you couldn't hear anything on 10 meters. Now you're starting to hear it.
Yeah. Yeah, I've been getting a few contacts on 10, pretty far away. Okay, so it's best at the 160, 80, and 40 at night. Whereas 40 during the daytime, because of depending on how much absorption in the D layer, you may not get too much.
It's also very noisy.
Oh yeah. The lower bands tend to be very noisy, especially if you're around power lines and things. They tend to pick up some of that noise.
Or charging stations.
And for some reason, a vertical, you would think wouldn't be, but verticals are noisier than horizontals
Really?
at those frequencies. Yeah. I didn't understand that. Still
I
don't.
don't understand it either.
But I think I saw an explanation that said most of the man-made noise, like power lines and machinery and stuff, tends to be vertically polarized. Why, I don't know.
You ever drive by Tesla down here?
No. Well, yeah, but
Have your AM radio on? It'll disappear on you.
because of the charging stations.
Yeah, when they're charging down there.
Yeah.
Okay, irregular fading. The ionosphere is constantly changing. I mean, its atmosphere, it depends on the ionization, depends on how much solar activity there is at the time. And it's kind of like, think of it as clouds, and it's not a nice smooth surface to bounce off of. It's lumpy. So sometimes, I mean, depending on what part of it you hit, you can't determine the angle that it's going to reflect that or refract that. I suspect it has different densities too. So because of that, you can get kind of a multipath because you can get two different reflections off of the ionosphere, and they may combine or they may subtract from one another when they get to the receiver. This is the big ARL band chart, which, and it's got a nice map on the back.
Yes.
I'm going to try to get some more of those. I'm almost out. They make me buy those. The other stuff free. Okay, so you just need to kind of get familiar with that. The farther you go, like general and extra, there'll be more questions about these little sections of the bands, which I can't ever remember. That's some of the stuff you just have to memorize for the exam.
Power limits. And they keep changing them too.
Yeah. Okay, what is generally the best time for long distance 10-meter band propagation via the F region?
See? Charlie?
For low sunspot activity?
Oh, those, okay. Hold on. I might have to read. Think they want to read them all, but
Yeah, you can cancel 2 of those.
Mhm.
What is the likely cause of irregular fading of signals propagated by the ionosphere?
Okay.
Kind of multipath. Polarization. On the HF bands, it isn't nearly as critical as it is on VHF and UHF. Like we showed with the handy talkies, if they're cross polarized, you hardly pick up anything. Where in HF, things tend to get elliptically polarized, whether you want to or not. So it doesn't really make much difference, especially if you got propagation where it's being refracted. It's definitely not going to come back the way it was sent. Which of the following results from the fact that signals propagated by the ionosphere are elliptically polarized? Okay. Coffee break, pee break, and then we'll see if we can contact somebody. Oh, I told them around 11. That's not too bad. 11:10. Even though we didn't hurry. There's coffee.
I got water.
There's snacks.
No,
I'm
I
gonna
got
have,
enough fat.
huh?
I got enough fat. I don't need any extra.
yeah, all that free food we get over there is just bad for the stomach.
I don't know. These are awful good.
Oh, thank you for doing this.
No problem. It's the least I can do.
What's the most you do? I don't know.
Roger,
Yeah,
at the office, we have Office 365 on those, or the new,
yeah, yeah.
because they have automatic save on them. And that may be what the problem is.
Yeah, Office 365 will do a save automatically to the OneDrive. If you don't want it, do it.
You gotta turn it off.
You gotta turn it on.
And maybe that's what some of the problems we've been having.
That and Adobe came out with an update. Didn't tell anybody about it and it creates a shadow on there. So the next time you bring it up, it's crap.
That's-
But as soon as you type in, it all disappears. I don't know.
But then it ends up printing out the wrong one.
I can tell that.
Well, that's what was happening the other day.
It stays for the print.
It would come up on the screen correctly,
Yeah.
you say print, and it would go back and print the other one.
Too good.
Okay, no. We had to end up filling out page one by hand.
Yeah.
And so I think about it last night when I was working on something else. And the damn thing was auto saving on me. I didn't have it turned off.
So you had the same problem at home?
Yeah, but at home it's different, you know. I didn't have the printing the wrong one out. But it was saving everything that I was doing. I didn't know it was saving it. I don't know that much about it. How?
We've been working with Dell to try to straighten out the living room space problem.
Mhm.
And next Thursday, we're gonna meet, we got a planned upgrade on the Dell hardware.
Hmm.
That one of the stations that went out, he's supposed to come in with a technician and fix it. Interesting.
That's SARNet. It's a network of receivers, most in Florida, into Georgia, are all interconnected. And there's a repeater over in Cocoa as part of that, which is what this one's on.
This is K1 CPO. Anybody in the room? No.
That's a,
Yeah.
the cable you have on that.
I get asked, good morning, Dave.
Yeah,
You're
I
here
just didn't
at,
take it off.
Over.
What?
That's Dave's repeater.
Oh. Dave, this is Bob.
That's down at Courtney's place. Where that. That's where that
On
repeater,
one of their buildings?
up on the 13th floor.
Yeah.
Did he say he was working?
He's working, yeah, that's why may not be able to answer right away.
Go ahead.
He said, go ahead.
Yeah, this is Whiskey 3 Romeo Delta Lima. Are you free at a moment?
At the moment. Like,
We're doing good. We finished first section about on time. So far, they got most of the questions right.
Yeah.
I imagine most, yeah, okay.
That isn't a 10.
Okay, I'm gonna let them chat with you a bit, see if they got any questions for you. Dave is our kind of repeater expert in
One of them, yeah.
I don't know, I'm trying to think of something to ask him. Where's he located?
She's at Courtney Springs,
I don't even.
right down by the airport here.
Oh, okay.
Is he one of the inmates over?
I'm sorry,
Is he a resident?
no, he works there.
he works there.
No,
Well,
I don't know. What do I ask that guy?
You got a question about amateur radio? He'll have an answer. Or UFOs, he's big on
oh,
UFOs.
yeah.
This is student Steve, wondering if you have an opinion on amateur radios handheld for new guys.
Welcome to, Ham Radio. Yeah, I would go with the budget session to begin with. It's definitely make sure you find something that's rated, and approved. And then you can turn line right down, Southend 9R, and I got a organization. IRL.
Somebody else come on. Same time.
$1,000.